All right, welcome back. Today I'm joined by Professor Jessica Kramer at the University of Utah, which I'm very excited to be joined by her today because she really does a lot of really interesting stuff and kind of the interface between bioengineering and but with a lot of emphasis on chemistry. So it should be really fun today. Well, thank you again for coming on today. I guess where we can get started is that is kind of your background. So I know that you actually started at the University of Utah as an undergraduate. So I only imagine that you kind of are from that area. I imagine the Pacific Northwest. So I don't know if you want to tell us a little bit about yourself. Get going.
Sure. Yeah, it's so great to meet you and really nice to be part of your podcast, Aiden. I am originally from Utah, so I'm one of the lucky faculty that found a job back home, which is really nice. And Utah is a really special place because we can do top quality research and have access to a world-class university, but also world-class skiing and national parks and all four seasons. Sorry, my dog is barking, of course, like, Zoom and podcast things from home. um, so another
Listen,
cool
that's
thing
the way
about
it
Utah
goes.
is
It's
you
all
can have a
good.
big backyard with a bunch of dogs. So I actually have three dogs. And during the pandemic and
Yeah.
when we did Zoom teaching, my dogs would like often appear to cheer up the students, which was nice.
Yeah. Well, it'll be the first time we get a dog to appear on the podcast. So, if anything else, that'll be a great sight to see. Um, Now, do you
Well,
ski
great.
yourself? Are you kind of a winter sports type of person or outdoors
Yeah,
activity
so
in general?
I grew up in Utah and I learned to ski when I was about 4. And I learned to snowboard when I was in high school, and I still enjoy doing both of those things. And we're really lucky here because we can go skiing, say early in the morning, and then we can go into lab and really be there by like noon if you're lucky. You can go in and make a few ski runs and then turn around and come into lab. So it's pretty special.
I've actually never heard that type of dichotomy before. It's definitely certainly one of the negatives of being in Texas, at least in Houston, is it's so flat. Um, like there's hardly any like real nature around here, which is a bit unfortunate, but it is what it is. Um, so that's pretty cool and definitely relatively exclusive to University of Utah. Um, Growing up, or uh, I guess approaching as an undergrad at the University of Utah, did you have like any initial interest in STEM and biology and chemistry, or when did that all those sorts of like initial inspirations start?
Mm. Yeah, it's a good question. I think early on, I wasn't aware of what a research lifestyle would be like and what, academic labs were like. So, like many folks, I thought I'm interested in biology, I'm interested in human health, and so I should be a medical doctor. And so I went through a lot of pre med courses. And along the way, of course, I took organic chemistry. And the first semester of organic chemistry was really tough and challenged me, and I had to study a lot. And I'll say that my interest in STEM was really sparked by my first organic chemistry professor, where I actually took a transfer, or we can do exchanges. The University of Utah allows exchange years, and I really wanted to live in the redwoods. I wanted to live near the ocean and the redwoods, so I took an exchange year at Humboldt State University, which is in far northern California. And it's small, it's a small school. And so my organic chemistry class was very small, and the professor was very involved. His name was William Wood, and he's really the person who sparked my interest in chemistry and in research. And so he would take us to the greenhouse and show us plants that did really cool reactions we'd talk about in class. We'd like go looking for stink bugs. He taught us how sunscreens worked, and he was wonderful. And by the end of organic chemistry, I was, at the top of the class because I loved it so much. And so Professor Wood ended up connecting me with a colleague in Utah who he had done his postdoc with. And that colleague had a company in Utah. And so I started as an intern there when I was 19 and started doing research as an undergrad. And that really never looked back. I kind of forgot all about medical school at that point.
I feel like it's got to be something like 75% of like people start out as like attending to go to medical school, but then you just find a passion for, let's say, I would say like fundamental sciences. Not that medical school is any less difficult, but I feel like you have a more fundamental understanding of the science. That's really interesting that you're able to do, what was it called? It's not really abroad, but like you were able to go study like at a different university for an entire semester. Is
Mm-hmm.
that how it works, or how did that work? That's definitely a unique thing
Yeah.
I've never heard of before.
I don't know the extent of the schools that participate. It's not unique to University of Utah because there were many schools that we could
Mm.
exchange to, but I believe you could do a semester or a year. So I did a year, and you could apply for an exchange program. And if accepted, I think there's not much to it other than being in good academic standing and having a desire. And you can pick a list of from the list of participating schools, and there were many. And some of them were abroad, some were national. And you could choose to either pay the in state tuition at the host university or your normal University of Utah tuition. And then the credits would automatically transfer back to your school. So I chose to do 1 year, and it was really a good experience. I think it broadened my horizons. Obviously, led to an industrial position, and like changed my whole career path. It happened from that exchange, and so I think it's a great
Yeah.
opportunity if people have the desire or means to try living somewhere else.
Yeah, I think I had to look up Redwoods National Park. 'Cause I was trying to get a sense of like where that was, and yeah, it's really up there in Northern Cal. How did you like? I'm sure it was beautiful scenery for one, but like how did you stumble across that university? Like what was the appeal for that other than like getting, I would say, get away for Utah maybe for a year?
Yeah. Well, it is a small school, so I'm not sure I would have heard of it, except I had a family member who had done his undergraduate degree there and always talked so fondly of the beaches and the redwoods, and also the small class sizes and the emphasis on teaching, because they don't, I don't believe they actually have any or maybe many PhD granting departments there. They do have master's degrees in some departments, but it really is focused on undergraduate education with undergraduate research experiences and small classes. And so that was really appealing, because my first year at the University of Utah, which is a very big school, I had a traditional Gen Chem class where there's hundreds and hundreds of students, and um, so the small class size was appealing, as well as kind of living in the opposite climate that we had here in Utah, where there was like misty, cool air and beaches and big trees.
Right. But in the Pacific Northwest, though, could you really go into the beach? Like, could you really like surf and swim, or is it like it seems like it would be too cold up there? No,
It's pretty cold.
or is it
I
just
did
a
try
sacrifice?
surfing
Yeah,
many
fair.
times. Actually, I learned to surf originally there in those cold, cold beaches where there's sharks and redwood trees floating in the water. And so I thought surfing was really, really hard. And it's true, but not as hard as trying it in very cold water. But you can certainly swim and surf with a
Fair.
wetsuit. And there are a few really magical sunny days every year where you can go to the beach and, maybe lay on a towel in your suit.
Yeah. Well, that's certainly a great opportunity, and really glad you shared that, because I feel like you know, for people that are listening, I mean, to go out and see if like what if they could study, another university for a year, I think that's definitely a very unique opportunity for people, to see what's available there. Now, I also so that experience there led you to do some undergraduate research back at University of Utah with Professor Poulter. or was that at the other university?
Dale Poulter was at University of Utah. So I started research when
Okay.
I came back to Utah.
Okay. And what did you work on as an undergraduate there?
So when I first moved back from Humboldt State University, I started working at a company called Echelon Biosciences in the summer when I came back. And
Okay.
Dale Poulter was actually on the scientific advisory board along with another University of Utah professor, Glenn Presswich. And the two of them had contributed to starting this company that was kind of, I think, originally in an incubator space next to the university, and then eventually got their own lab and product line. And they are still in business today, selling some key reagents that I helped to work on. And so the company specializes in making phosphoinositides and other membrane lipids that are glycosylated, and they're really important for signaling and of great interest in cancer and a few other pathways. And so the company was selling reagents for studying that kind of biology. And they also had a product line studying isoprenoids. And so many first year organic students will know the isoprene unit, which is a building block for cholesterol, testosterone, and many types of those types of molecular scaffolds will all come from isoprene units. And so the company also had a product line with intermediates in those biosynthetic pathways. And so I started as a chemist when I worked there. And eventually, as part of my undergraduate honors thesis, I needed to do a research project. So I worked with Dale Poulter in his lab to study the binding specificity of one of those membrane lipids.
That's really awesome. You're able to do that. Yeah, I know that. What mind just telling us briefly a little bit about the phosphoinositides? Hopefully, I pronounced that rightly. It's a bit of a I'm not. It's a bit of a word jumble. Phosphoinositides.
Yeah,
Mind telling us a
phosphoinositide.
little bit about what they are and kind of like they're making phosphoinositides. Mind telling us a little bit about what they are and what they're generally what they're used for.
Yeah, so in our cell membranes, right, we have a mixture of different lipids and cholesterol and various components that are a part of the cell membrane. And so phosphoinositides are a minor component of the cell membrane. I believe 10% or less of the lipids will have that type of head group. And so like everything really in glycobiology, it's really complex because of the different sugars and sugar modifications that can be attached to whatever molecule of interest that's glycosylated, in this case, a lipid tail. And so those inositides can have different phosphorylation patterns. And so around that ring of carbon-oxygen groups, you can have phosphates stuck at different positions. And that, of course, changes the size, shape, and charge of the molecule, and it will therefore bind to different proteins, specifically based on the phosphorylation. And so what I had worked on with Dale is looking at how proteins that actually come up to the cell membrane chop up these membrane lipids into their sugar and lipid parts. And we studied how the phosphorylation patterns affect whether or not they'll be chopped up.
That's really cool. Yeah, I think what I find like probably most fascinating is that like all this kind of transpired, and even up until now, really, is because you did this opportunity at the other university. I mean, I think that this is like super fascinating. I think. So hopefully that's a testament to, or for other students to try that out, because I think that's really cool. But yeah, so you mentioned so you did an internship there, and you basically did your senior honors thesis kind of around this stuff. It must have been nice to feel like you had a nice secure job right out of college for sure. But after some time in industry, you actually did decide to come back to do your graduate studies at UCLA. and to get your PhD. What I'm curious about is, why, what were kind of some of the decisions to come back into academia? What was what was that spark for you?
Yeah, I mean, I think these are really big decisions that people make as they close in on the end of their undergraduate time or maybe in a gap year. And so for me, I had mentioned I was, of course, interested in medicine and medical school. And I think by the end of my undergraduate time, I had been working with the company and I had done this honors thesis. And I thought at this point, I started to very seriously reconsider what type of postgraduate work I wanted to do. And for me, I think, I got a lot of insights working at the company and doing a research project. And so I would encourage, everybody that's sort of agnostic or maybe even just unaware, like we don't know what we don't know. And so getting to know your faculty members, people teaching your classes, even your TAs, they're probably graduate students working on interesting projects. Getting to know some of the people and asking about what are they working on? What is their life like? What do they think what's that grad student planning to do later? And educating yourself about what your options are. And so I started to do that toward the end of my undergrad. I actually made a point to reach out to friends, family, colleagues that were physicians in different areas of medicine and kind of ask, what's your day like? What do you like and dislike about your job? And started to learn more about that. And of course, I was working alongside some PhD researchers, and I talked to them about what their graduate school experiences were like. And I started to realize that I wanted to be a knowledge creator rather than even just sort of a knowledge user. And I think that's a really key feature of what we do as academic researchers is that we create new knowledge. Like we go ask questions that don't have any answers yet, and we figure out new pathways and new information. And I really liked that element of discovery. And I also really liked the idea of coming out of my postgraduate school without debt, of course, right? And so I think the field of medicine it's tough these days because there's a huge financial investment that you have to make, and there's a huge time investment that's, I think it's different than what happens during graduate school in a chemistry or STEM program. And so for those reasons, I started to look into graduate schools and ended up deciding to go that path.
Yeah, I think you bring up definitely a few really good points, especially for within academia and graduate school. It really is a unique opportunity to just broaden your knowledge that can be lacked in industry. Not to say that there's not like certain cases where people in industry are, let's say, on the forefront of finding new knowledge, but I mean, for the most part, it's you have your objectives and you have things that you're making, but you're not necessarily pushing what's new. And there's nothing wrong with that, and there's absolutely nothing wrong with that either. But I think academia really, has that edge, I would say. But that's really cool that you took in all those aspects from people that you knew and decided to go back to graduate schools. I think those are really, really awesome points. What about, let's say, UCLA that kind of drew you there? And what other schools were you looking at? And then why decide to go into UCLA? And also, I know you worked with Professor Tim Deming. So, what were the decisions in joining his group and what you worked on?
Mm-hmm. Yeah, so I decided to apply fairly narrowly for graduate programs. I wanted to be back in California after my time as an exchange student. And I mainly applied to California schools. I have to say I like the outdoors. Coming from Utah, I was used to spending, I could go take my dogs for a hike in the beautiful mountains, like after work, and it was just sort of integrated into my day. So I wasn't thinking about living in the middle of New York City or maybe in the Midwest where it's really flat. So I I thought about moving to California, but I also wanted an experience with a bigger city and maybe some different politics and different cultures that we didn't have in Utah. And so that was also really important to me in thinking about where to go. And some of the factors that contributed to me picking UCLA is that LA is very multicultural. There's, Thai town and Japan town and Little Ethiopia and all of this amazing, rich cultural experiences that I didn't have in Utah. And along with that comes art museums and music and all the kind of like nice things you can do if you can ever escape from lab. So that was really important to me. But UCLA in particular has a really excellent chemistry program, and it's a big school with a medical school with very rich research history. And so there's a lot of collaborations that I could envision where it was just an environment that it seemed conducive to success. And I was very impressed with several faculty at the graduate recruitment event. And so those were all factors so it's a combination of like excellent research and being happy with your life outside of lab that I decided to go to LA for a few years. And I think, you made a couple of good points, about industry versus academia. And really, when I started at UCLA, I thought I will go here to get my PhD and I'll get enough knowledge and learn how to problem solve and learn how to lead. And then I can come back to industry and lead a team or develop my own products and things. And obviously, I ended up deciding to do academia along the way. And so there are some reasons where I think in industry, people are much more beholden to finances. You've got to seek venture capitalism, or you've got to turn a profit. And so while there are fantastic R&D departments that even publish regularly, like Merck or Genentech and some of these big companies certainly maintain some elements of academia. I think that's not exactly standard. And so, yeah, along the way at UCLA, I decided that my heart was in the sort of discovery and knowledge creation.
Yeah. I've never really been out to the West Coast in general. LA is definitely a city that I will visit it one day. I'll get to it eventually. But yeah, right. I mean, generally speaking, how was it? Anything that kind of surprised you when you first moved to LA? Because you're from the Utah area, and you also went to Northern California. Which relatively are kind of, I would say, they're kind of secluded. I would say you have to travel vast distances, I would say, to get like to really populated areas. But at LA, I mean, obviously, like all different types of cultures are there. I don't know why this stuck with me, but you mentioned like there's like Little Ethiopia, which a couple months ago, my friend who is half Ethiopian, half Italian half Italian, half Ethiopian, but he had all of us over to eat authentic Ethiopian food, and I was pleasantly surprised at the food. I had no idea what to expect. Obviously, I never had Ethiopian food before. It was super delicious. High recommend Ethiopian food for anyone that's listening. It was really good. I couldn't tell you what I was eating, honestly. He explained it to me, and I think there's a video of it somewhere of him explaining all the foods, but it was just really good, and I highly recommend it. But anyway, sorry, that was the tangent. But yeah, LA, I mean, generally, like, was what were some of the biggest? I mean, I don't know if culture shock's the right word, but like something that surprised you when you first like moved there. A couple of things that like just like you didn't expect coming from Utah.
Yeah. So I would say the homeless population in LA was something we just didn't have as extensive of a homeless population in Utah as we did in LA. Obviously, there's weather considerations and things. And so that was, really sad. And I would say more of like a shock when I first arrived there. And, I think continues to be a problem that San Francisco and LA and really every big city faces to figure out how to help people who are on the streets. So that was probably the biggest shock when I moved. And then maybe another shock was that it actually gets pretty cold in LA. And my house in Utah, we have like a furnace and a thermostat, and you just go to the wall and you type whatever temperature you want the house to be in your thermostat. Not the case in LA. Most of those houses are pretty old and they don't seal, and like the windows barely close, and there is no thermostat. And I was freezing. It was like down to 40 degrees my first winter there in LA. And I remember I opened the oven. I turned the oven on and I took my organic chemistry book and I like sat on the floor in front of the open oven trying to prepare for my synthesis exam. And one of my friends came over to study with me, and he was like, "Wow, it's really cold in here. Why don't you turn the heater on?" And I was like, "I wish I could. There's no heater." And he found this little, grate in the corner of the floor, and he said, "There's this thing is a heater. You need like a metal rod, like a key that sticks down in the ground to turn it on." And the key was missing, and so it wasn't obvious to me. I'd never seen this thing before. So we ended up calling the landlord, and they came over with the key, and I did get heat eventually. But that was another surprise. Everyone thinks that LA. Yeah.
That is really interesting. I would not have. I don't even know what that device is. Okay.
Yeah.
Look at that. I think definitely, because I kind of grew up in Philadelphia. And so, suburbs of Philadelphia, really. And now I'm in Houston. So I've kind of always, the homeless population is, it's kind of sad. In Philadelphia, there's Kensington, which, has a lot of issues with drug addiction. It's really quite sad to see. And honestly, I don't really know how you really fix these issues. I think, these people definitely need help. And somewhere to stay, and they need help. I don't really know how to, I don't really know any grand solutions to this though, especially I've never been to LA, but I've only heard stories of, it's gotta be the homelessness is super dense and packed in LA. I know Skid Row can be really bad. And I've heard that it's starting to basically expand the homelessness, and it's really a shame. I don't know how if you fix it. I think you got to get shelters in there for people, and you got to get people off the street. I don't know if the people like came into, because I know UCLA is kind of like Northwest LA, so I don't know if they encroach on like the campus, or they do a good job of keeping them off campus, or if there's somewhere for them to stay. But I don't know.
I think campus is very safe in general. I always felt safe on campus, even working late nights as a grad student. So I think that's all right. But it's just sort of a fact of life in big cities, especially in California. And I'm no expert in the solutions, but I know the pandemic has made everything even harder, and put people in really bad economic situations. And so hopefully there are really good experts on the city councils working on these issues for us. But that was a really memorable thing that I noticed coming into the state.
I hear that. Hopefully, we get you. All we really can do is, elect officials that will help with this. That's all, we can really do, I think. But having said that, though, like I mentioned, you joined Professor Tim Deming's lab. And so, what was the kind of research that you're doing there at UCLA in his lab?
Yeah. So, like most programs nowadays actually have rotations, and you can visit and spend do a short stint in a faculty member or two's lab before you join. And we actually didn't have that at UCLA in 2007 when I started the program, and I believe they do now. So my first semester at UCLA, I visited the group meetings, the lab group meetings of several different faculty members to kind of get a sense of what they worked on and what their students were like. And I went to coffee. I would ask the older grad students, can we go have coffee? Can I buy you a coffee? And can you tell me about the lab and your projects? And so I got to know some of the projects in the Deming lab, and it really seemed like very applicable use of chemistry, where I liked that I could do some sugar and amino acid chemistry like I had done in industry. And I felt like I could kind of hit the ground running with skills I already had, which I think is, always a good thing to kind of leverage whatever prior skills you have to do something new. And Tim Deming's lab, they did some really cool things with the chemistry, including at the time they were working on hydrogel formation. So polypeptides, long strings of peptides that were injectable. So they would form gels, but not so stiff you couldn't inject them. And they were working on central nervous system drug delivery and like wound healing applications. They were working on drug delivery applications. And so I could see this interface between chemistry and biology and material science. And I felt like I would both develop as a chemist, but also as a bioengineer. Tim was the chair of the bioengineering department at UCLA when I joined. And so I really liked the being able to see the translational aspects of the work we were doing. And
Right.
Tim's also a really nice guy. He seemed
Yeah.
like he'd be a person I would enjoy working with for 5 years. And his lab was, I liked the other students in the lab, and it was also big enough that I felt like I was in a team, but not so big that I felt I would be lost in a sea of like if you join a lab where there's 30 graduate students, you may not get a lot of one-on-one time with the professor. So I liked the size of Tim's lab as well. And I felt like I would get a lot of direction and support, but without sort of like, being under the pressure of being like one of two graduate students.
Yeah, I hear you. Yeah, you bring up definitely a lot of good points there. Picking an advisor is, arguably the most important. Well, I probably single-handedly is the most important thing a graduate student can do. I know a lot of people say like the school is not as important as your advisor. I would say, and I tend to agree with that. Actually, I think the advisor is extremely important, and the questions of group dynamics. Are you gonna like people that you work with every day, whether or not and are you happy like in their presence, right? They're there. Can they offer great advice? And you bring up a great point too. If you're in a large group, are you going to get that one-on-one time with an advisor? That is, extremely important for young graduate students, right? One counterpoint is, if you have a big group, there are a lot of, upperclassmen or higher level graduate students or like postdoctorate researchers there that can also offer great insight. Mm-hmm. So those are really good, things you bring up there. And I also really like what you said about really the interdisciplinary between bioengineering and chemistry here, I think is really what's cool and really what caught my attention, I think. Because at some levels, it's like, I'm an organometallic chemist, and it's really fun to think about, I'd say, fundamentals of organometallic chemistry. But the flip side is like, it would be nice. It's really nice to see this sort of chemistry in real world applications, right? So I think that is always that kind of thing to consider too, is how much it's nice to have like real world impacts, I would say. And so that's really cool. Now, during your time there, what were you working on personally? Like, what was kind of your what was your thesis really?
Yeah. So I had two major projects and areas I worked on during my graduate studies with Tim Deming. And One major area was glycopolypeptide synthesis by NCA polymerization. And so what we did is couple sugars to amino acids and cyclize those amino acids into 5-membered rings. And those rings had a carbonyl oxygen bridge called anhydride. And that is quite amenable to ring opening and loss of CO2. And that drives the reaction forward. And so you end up forming peptide bonds. And it's a very old chemistry that's been known for about 100 years, actually more now. I think maybe 1906 is the first report in the literature of these cyclic amino acid derivatives being used to form peptide bonds. And so for any of your listeners who have done solid phase peptide synthesis, it's fairly automated. It's pretty easy to do. You do HPLC when you're done, but you can't make really long chains, especially if you're interested in post-translational modifications like sugars. You can't get many sugar molecules on that peptide. The yield will go down and down. They'll get tough to purify, and you'll end up with something. It can be a pretty heroic effort to make even a few milligrams of something that's 10 residues if you've got sugars on there. So what Tim Deming and I wanted to do is to use this polymerization method to make glycopolypeptides. And so what's really cool is that NCA, these anhydride molecules, you can do these polymerizations on multi-gram scale if you want. We didn't really have cause to make that much for an academic project, but it is used industrially for an FDA-approved MS drug, and also for various bioreagents, like to make polylysine and things. And so it's quite scalable, and so we could make milligrams to grams quite easily and very quickly too. And so we could, these reactions, we actually use an organometallic initiator. It was sort of one of Tim Deming's big contributions to the field of NCA chemistry, is developing nickel and cobalt catalysts that do these reactions very efficiently. And so you can tightly control the length of the peptide chain. So you could make a 30 mer, a 50 mer, a 500 mer very quickly and on scale. And so one part of my PhD research was to develop that chemistry with sugars attached. And then the whole second area of my dissertation, which I published many papers on, was methionine chemistry, and making methionine-based polypeptides from the same NCA cyclized amino acid route, but with methionine. And so methionine is a unique amino acid that it has a thioether in its side chain. And the thioether can undergo some unique chemistry. And so we could take this single structure that is either all methionine or methionine rich, or even a few sites of methionine, wherever methionine is present, and you can treat it with peroxide and form sulfoxide or sulfone residues. Okay. And that will totally change the solubility. And there's some reasons why that's really nice for non-ionic, sort of natural, kind of biologically based polymers that have properties that are PEG-like. And so if your listeners have heard of PEG, which is sort of like this ubiquitous polymer that is conjugated onto like all kinds of drug delivery formulations, or even like you can gobble it up by the spoonful as like I think it's like a laxative or something. So their PEG is like everywhere, but it turns out there's some downsides, both immunologically and otherwise, to PEG. And so we need alternatives. And these oxidized methionines are great PEG alternatives. And then we also developed some chemistries using methionine to do reactions that are forming sulfonium compounds. And so you can alkylate thioethers, including the one in methionine, with a variety of electrophiles. and install all kinds of groups of interest very, very easily. And so we developed these methionine-based bioconjugations, and they really have a lot of kind of click-like characteristics in that they're very selective. They don't care about pH because the nucleophile of a thioether has no proton to gain or lose, and so it's not pH sensitive, and therefore, in acidic pH, amines and thiols and things you would find in proteins will not react with electrophiles. You'll only alkylate methionine. And the reactions are quite broad in scope and highly efficient. And so we used methionine alkylations to install sugars or fluorophores or, clickable like alkyne groups, whatever types of things that you want on peptides and proteins. And so those were the two areas that I worked on in my dissertation, was methionine chemistry and glycopeptide synthesis.
That's really interesting. Yeah, because just on that, I mean, methionine, especially like the thioethers, don't really strike me as a great nucleophile. So is it easy to alkylate those things, or do you have to use a very sensitive electrophile, or is it pretty easy synthesis?
They're actually pretty easy. They're actually pretty good nucleophiles relatively. It's not exactly, I guess, a very well-known or commonly used, these sulfoniums, as nucleophiles, but they're actually pretty good. So you do need some sort of a reasonably reactive electrophile. If you have a poorly reactive electrophile, they generally won't proceed without use of some kind of catalyst. And so in that case, if we had poorly reactive electrophiles, we could promote those reactions with the use of silver salts like silver triflate or silver tetrafluoroborate. And we could get poorly or sort of less activated electrophiles to react with methionine. But there are many, many useful electrophiles that just directly react with methionine in water. So some of our favorites are like bromides, things that are adjacent to an amide or a carbonyl. So some derivatives of bromoacetic acid. You can use bromoacetic acid and conjugate all kinds of things, make amide bonds there, and that structure reacts beautifully, even in a 1-to-1 ratio with methionine. And you can do it at like pH 2 or 3, where nothing else in a protein or peptide will react. And it's quite efficient.
Wow. That's pretty cool. Does the concentration of the thioether matter? Like, let's say in a long chain, you have like, I don't know, I'm not really a polymer chemist, but let's say a low concentration or a low density of like methionine. Or do you need like a polymer? Do you need a chain with a lot of methionine? Hopefully that makes sense. I'm describing it right, but
yeah,
does it not really
I'm
matter?
Sure that everyone you can think back to your like physical organic courses where the molarity and the concentration of each reagent affects the rate, the kinetics, right? This is all part of the equation. So you're going to have your rate constant and your reactant concentrations, and that's going to tell you how long your reaction is going to take. And these reactions are not as fast as things like you would see with the transcyclooctene tetrazine ligations and super, super fast bioorthogonal conjugations that can proceed at very, very low concentrations. So I don't think we would ever propose to use those type of reactions for like in vivo tagging of low abundance proteins the way you can, for example, like a Bertozzi, azide cyclooctine or a tetrazine cyclooctene reaction. But in vitro, for example, modifying an antibody, pulling down methionine containing proteins for mass spec analysis for proteomics, things like that, it's absolutely fast enough. And the reactions will typically proceed in a few hours, even if you have like a single methionine residue in a peptide, and 1-to-1 equivalent of your electrophile to the thioether.
Yeah. Okay. That's the right nomenclature. Residue per. That's the right one I was looking for.
Mm-hmm.
That's really awesome chemistry. Now, did it all work perfectly, or did it like go sideways, and like were there kind of points where like, I don't know, do you like remember like moments where it's like, oh my god, this is working, or did it work, was it kind of a sludge for a little while before getting something to work?
Yeah, I think every graduate student goes through phases in their research where there's a lull or like things are just not working for a while, and you try the same thing over and over for a while, thinking maybe it's your hands. Or then you try modifying each
Yep.
reagent or each step one by one, right? And we all go through phases like that. I certainly had that in both projects with the amino acid work and the methionine work. And there are a few things that I decided just simply don't work, or they're not worth the effort to figure out, that the juice wouldn't be worth the squeeze. And so ended up, shifting. And I think that that's a good skill that you can learn and develop as a graduate student, is sort of when to throw in the towel. And that's, a good
Mhm.
advisor will help you figure that out too.
Yeah. Do you have to go? Do you have to go at 3, or
We've still got 10 minutes, but I can stay on a few minutes longer.
okay?
I don't have any meetings
Okay.
after this,
Yeah,
so
definitely, because
we're good.
I, for, I forgot. I just want to make sure. I definitely yeah, for the sake of time, I definitely want to jump then to your research now, because I think that stuff's super cool. And then we can kind of maybe backtrack then too.
Mhm.
But yeah, like we said at the beginning, so now you're assistant professor in bioengineering at University of Utah, and you guys do. I mean, your group does really cool stuff, really in like biomimetic materials. A lot of stuff, I guess, with like kind of like, I would say, mucus chemistry. I guess that's I'm gonna
Mhm.
put that. I'm gonna make that a phrase. Um, Cadillac engineering. And I guess, I guess I'll kind of let you take the reins here a little bit to explain your research, and we can flush it out a little bit. So, but I think it's really cool. So I'll let you take it away.
Well, thanks, Aiden. We think it's really cool too. We're very excited about the projects, everyone on my team, and a big area of focus, not the entire lab, but a big area of focus is, as you say, mucus chemistry and also mucus biology. And I got really excited about what most people consider as a waste product. During my time as a postdoc in the Bertozzi lab, they were studying the proteins in mucus. So they're called mucins, aptly named. And they were studying these proteins mainly for the interest of cancer, actually. And so that's what sparked my interest in the first
Hmm.
place. And now my lab studies how these mucus proteins interact both in to contribute to cancer, but also we got very interested in coronavirus infections back in 2020, and we've started to make some contributions there as well. And so we're interested in both the sort of biology, like why and how do different structures found in these mucin proteins, what do they do in cancer? What do they do in viral infections? And we're also really interested in the chemistry part, which is how do their molecular structures, how are they affected by the sugars that are attached to the proteins? We have a lot of
Hmm.
different sugars that are attached to these proteins. How do they affect both the molecular structure in terms of the protein conformation, but also binding events to things like coronaviruses or maybe immune cells that would be able to recognize cancer? And so a big chunk of my lab is working on synthesizing mucins from chemical methods. It turns out that if you try to just get mucus from biological sources, and people love to offer to give my lab mucus, it turns out that that's useful for
That's an
some
easy joke
experiments.
there.
Yeah,
Yeah.
but it's really tricky because we have many different genes and that contribute to the protein backbone that are mucins. But then, aside from having many genes, we also have enzymes in our cells that add and remove sugars to those proteins. And so that combination of different protein structures with different sugar patterns leads to a whole different mixture of mucin structures. And it becomes very tricky to identify structure function relationships or to have models where we can test out things like viral infection, or even like if you swallow a drug, will it penetrate the mucus in your stomach and intestines and get inside your cells? Can we even swallow this drug or not?
Mm.
And so my lab got really interested in using chemical methods to make one by one structures that we think are important for those types of events. And so there are people working on the chemistry to develop these sugars and put them onto our amino acids that we make these long polypeptide chains with. And then there are people that are working on the biology of these events that I mentioned. So that's a big area.
I think it's really fascinating because, yeah, I one thing I definitely want to point out too is like I feel like a lot of like maybe non-chemists or like non-STEM people might think like there is no difference, let's say, between making these glycoproteins synthetically versus what's in our body, right? Like I definitely want to make that clear. Like whether you make it chemically or you extract it, let's say from humans or living organisms, they're the same chemically. So you never really have to worry about, I don't know, its structure, I guess. Like it's the same thing. Now, what I found, what I thought was really interesting is that I saw a recent publication on, the mirror image mucins that I thought was really cool because I think what's one of the most fascinating things about, let's say, chemistry and biology is like the how the enantiomers, right? So of things can be extremely important in biological systems. So I think in you guys made these enantiopure glycoproteins or sugars, and like one enantiomer basically binds to proteases and the other one doesn't. Do I have that right? I should make sure that's
pretty close. Yeah, we did make some mixtures that are not enantiopure, but all mucins found in humans or other biological sources are based on L amino acids. So they have a specific orientation, right, of all the atoms around that central carbon. And that's how all life it has evolved to have our proteins on planet Earth. And so because we have those types of structures, we have evolved proteins that recognize those structures and are able to not only bind, but then break down those proteins and digest them. And this is really important for mucins because it's a surprising fact that we produce about 10 liters of mucus every day in the human body. 10 liters. And so
10 liters?
Yes,
oh my
10
God.
liters. That is a reasonable estimate based on the surface area that we have in the human body. So everything that's essentially not skin is covered with mucus, and that's how our stomach doesn't digest itself. Why our eyes are not stuck shut and our internal organs are not stuck together. They're coated with slippery mucus proteins. And of course, we cough, we sneeze, we cry, and then we also digest in our stomachs, and the mucus is lost there. And we have a microbiome, a collection of microorganisms that live in and on us, and they also eat up our mucus and use it as a food source. And so because of all this, we produce about 10 liters per day. And so, as I mentioned, my lab's thinking about making models of things like viral infection or cancer. We're also interested in mucin-based therapeutics. Like, can we lubricate dry eyes? Could we make anti-infectives that block viral adhesion to cell surfaces? And if you do that, you don't want your mucin to be degraded very rapidly. You want it to stick around and continue to lubricate or protect. And so to circumvent this degradation problem, we came up with using the mirror image of the amino acid found on planet Earth and using the opposite chirality, which is we don't have proteases evolved to recognize that. And so we essentially have the same sugars displayed in the same way, where they can bind to proteins that bind to sugars or maybe a virus, if that's what you're interested in. But the protein backbone itself is not a substrate for proteases, and it can't be broken down. And so we showed that they'll stick around for a very long time. And we could also tune how long they stick around by blending in some of the natural amino acids that we would normally have. And then they can slowly become substrates for those proteases again. And so we can kind of choose if we want it to be inert or slowly degrade.
Yeah, that's all really cool stuff. I guess one other thing I wanted to ask is like, how do you? First of all, I mean, 10 liters of mucus. How do you? If we have like so much different types of mucus, let's say inside of our body, how do you do you pick like what, let's say, mucus substrates you analyze, or are you guys kind of keeping it broad at the moment, like, are you kind of open to all sorts of mucus inside of our bodies, or do you kind of pick which ones you like to study?
Well, we're really excited about understanding cancer and viral infections are like two of the most
Okay.
exciting and important areas of mucus research that we're interested in. However, we're also thinking about other pathogens like fungal infections, bacterial infections. And so we're very inspired by the work of careful biologists who have taken apart these mucus components in the case of infections, and they have found certain sugars are maybe overexpressed, or maybe they've chopped off all of the sugars, and so they're not on a protein anymore. But binding studies have been done with sugars that are free and not attached to a protein, and so we look at those kinds of research studies to inspire the designs for our structures. Yeah. And so
Okay.
it depends what kind of tissue you're looking at. So like the eyes will have different mucus structures than those in the stomach, for example. And so we try to think about what tissue we're looking at and if there's any data at all about what sugars are important for binding events.
Well, I gotta imagine that it's super difficult to, well, one, synthesize. I'm sure synthesizing these polypeptides can be difficult, but anything so far that you've learned, like generally speaking, of how these, using your polypeptides to study these cancerous events. Anything you've kind of learned so far? Is that something ongoing in your lab right now?
Yeah, these are ongoing projects, but some of our initial studies have yielded very interesting results. I can speak to a recent paper from, gosh, I guess it was maybe a year and a half ago or so now, about coronaviruses, which ended up getting into the popular press because we talked about surface transmission. And so people, of course, were wondering if you need to wash your groceries or leave your mail in the mailbox for several days. And we ended up finding that mucins and specific structures of mucins will inhibit viral infection. And so we don't think that they like decompose the virus, but what they seem to do is coat the virus, and it can no longer interact with your cell surfaces and get into your cells to reproduce. And this is very much dependent on the sugars that are attached to the mucins. And so some forms of mucins will protect and some will not. And that's one interesting story where we know the structure is really, really important. And then in just probably the next month or two, you'll hopefully see a paper that we are working on right now be published about the role of mucins in cancer. And so if we think about cancer and tumor formation, we have cells that are rapidly growing and dividing. So much so that they're, instead of popping out of the cell layer, they're piling up. So the cells are piling up and growing and forming a tumor. And what we've shown in this recent study that is not yet published is that these mucins, when overexpressed and sort of underglycosylated, will induce a tumor-like structure where these cells pile up and start to do some really strange things. And we've correlated that to the effects of a mechano sensitive ion channel in the cell membrane, which is really interesting because it seems that these mucins that are really big, bulky proteins covered with sugars, they're very stiff. It seems to affect the mechanics of the cell membrane and affect these types of extrusion events and cause this tumor-like behavior. And so that's a couple of recent examples of things we've learned that mucins can do in these disease states.
Well, Professor Kramer, I want to thank you so much for coming on today. It's extremely pleasant talking to you, and I really look forward to your future work in these mucins. This is definitely an area that I'm really unfamiliar with, but I'm always excited to see. And so I look forward to what comes out of your lab over the next few years, I guess, hopefully. So
hope so too.
We're excited for that, and thank you.
Yeah. And before we jump off, I'm happy to, I know you mentioned wanting to chat about my time in Carolyn Bertozzi's lab. If that's something you want to include in your podcast, I'm happy to stay on for a couple more minutes for any questions you have about that.
Yeah, I definitely do. Thank you. I think, well, first of all, I know you, at what point did you want to go do a postdoc? Because, I assume at what point did you want to go do academia, I guess, because most people that do postdocs end up doing academia. And then obviously, well, maybe not obviously, but, Professor Carolyn Bertozzi is a Nobel laureate in 2021 for click chemistry. And so I'm very curious about, well, one, the work you did there, but also, at the time, was there, I assume there wasn't really any talks of winning the Nobel Prize, or it was just simply we're just interested in the chemistry. And so I'm kind of curious about that kind of dynamics as well.
Mm-hmm. Yeah. So toward the end of my graduate work, I started to think more seriously about running my own lab because I really enjoy doing research. I actually like writing. I think writing grants and papers is, yes, it's a task that can be tedious, but it's also fun. You really learn to tell stories and to really take a deep dive into a whole field of study to understand everything that other people have done. So I enjoyed that. I thought, okay, I might be interested in academia. I'll do a postdoc and keep that door open. And I became very interested in glycobiology because I'd been working on these glycopeptides, and I thought I can make surrogates for things found in nature with this chemistry. And so I joined the lab of Carolyn Bertozzi to do just that. And in the Bertozzi lab, there certainly was no talk of the Nobel Prize at that time. And I can certainly say Carolyn is not motivated by seeking prizes or anything really, but a pure passion for science
the
and solving
accolades.
problems. She really has an amazing mind for picking important problems and important projects. And her lab is filled with people that I think share that vision and really have a great team dynamic. And that was also inspirational to continue on in academia after kind of being under her leadership. She has a great example of how to run a lab.
I think that's super fascinating. Because I feel like a lot of young impressionable graduate students, I feel like a lot of them get caught up in the fame of it all. And on one side of it, it's it is super inspirational to see scientists that you work with, they get the recognition of, let's say, the Nobel Prize. And that's super fascinating, right? But on the other side of it's I feel like many scientists don't envision themselves as they don't do this sort of grandstanding type of thing either. So it's kind of it's very interesting, I think, to think about. It's on one hand you can use it as inspiration, but it's also really inspiring to see that if you just stay interested in the science, I mean, you can go really far. I think it's really a testament to, Professor Bertozzi, I think. So that's really cool.
Mhm.
And yeah, I think that's really fascinating. Were you interested now? Was the Bertozzi lab interested in glycoproteins specifically, or was this kind of a project that you wanted to pursue, and or were there kind of already ongoing projects within the Bertozzi lab that kind of helped you facilitate those topics?
Yeah, there were ongoing projects in mucin biology and also in glycopolymers in her lab, and that was part of why I wanted to join. Is that I thought I could contribute my skills to making better and better glycopolymers and better models in the systems they were interested. But also, I really wanted to learn biochemistry and molecular biology techniques that I had not developed during my time in an organic chemistry program. And so in her lab, I learned to clone, I learned to culture cells and do microscopy and do transfections and all kinds of, sort of typical things, but, not things that you might get in a traditional chemistry lab. And so that was really good, I think, for both of us, where we could each benefit from each other's skills. And in her lab, there were already existing mucin projects, and I have to give Carolyn a lot of credit for expanding those projects. Even after I left, she's done amazing things with mucin biology, particularly in terms of discovering mechanisms that mucins are involved in cancer and new therapeutic modalities to alter and disrupt those interactions. And hopefully we see some, new cancer therapies coming out of those projects in the next few years.
That's all really exciting. Then the last thing I want to pick your brain about is like what sort of things have you learned from Professor Bertozzi that you kind of bring to your lab now, and what kind of things do you try to emulate?
Mm-hmm. In terms of leadership style and kind of group management, I think Carolyn really tries to take good care of people in her team, and worry about people first, and money and resources second, and just figure it out how to take care of people. So I do my best to do that for my students, because graduate students certainly, you have a stipend, which is much better than a medical student, right? But it still is hard to make ends meet when you're in an expensive city. And so I try to take good care of people in my lab the way that she did. I would say, and scientifically, Carolyn has a really good eye for picking important projects and asking big picture questions. And if you can't answer the big picture questions, it's probably not a project or you should reconsider what you're doing. And so that's always really fundamental, is what we're doing really important or not? And I also can say that Carolyn, at some point she said that 70% yield is good enough, move on. So I think this is good advice in some ways, that, we can often, I think our field attracts perfectionists. In some of us anyway. I'm often guilty of this, wanting to make things perfect. And it turns out, sometimes
Right.
things are just good enough, and to really be discerning about what needs to be perfect and what doesn't, and kind of deciding when things are good enough and moving on to what is really important. So those are some pieces of advice that I think I really enjoyed from being in Carolyn's lab. But her lab is a really fun place to work, and we do some traditions and things in my lab that are inspired by things in her lab. She did top 10 reasons that someone should leave the lab when they're ready to go. And so we kind of roast people a little bit, which is fun.
That's amazing. Really good to hear. Yeah, I think it's definitely it's quite a person to get inspiration from, and to go. Now you're an assistant professor. It's great. I mean, that's great time there, right? A lot of things to learn from her. That's really cool that you had the opportunity to do that, for sure. But yeah, Professor Kramer, I want to thank you so much for coming on today. It was like I said, it was super pleasant talking to you and getting to know you. And I look forward to seeing, what comes out of your lab with these mucins, over the next few years. And that's super, super cool. And, I look forward to it.
All right. Well, thanks so much, Aiden. It's really been a pleasure chatting with you and learning about the podcast information that you're trying to share. I think it's a great project.
Hopefully we are able to keep it going strong. So, whatever. All right, everyone. This other episode. Thank you. See you next time.
All right.